AI paper slap. The paper is Qwen-VLA, a unified embodied foundation model by the Qwen team. Look, if you're building an embodied AI, you know the field is historically incredibly fragmented.
Yeah, totally siloed.
Right. We build different models for manipulation, completely different architectures for navigation, and, highly specific setups for different robotic arms. Well, Qwen-VLA basically shatters this by unifying everything into a single vision language action, or VLA, model.
A true generalist approach.
Exactly. It takes the natively multimodal Qwen 3.54b and uses it as the cerebrum for vision and language. Then a 1.15 billion parameter diffusion transformer, a flow matching decoder, basically acts as the cerebellum for continuous action.
But the massive breakthrough you really need to care about here is the training recipe.
Yes, they solved the dimensionality gap between text to action through this wild 4-stage process. They start with a text to action phase that deliberately hides all images, which, forces the model to learn a pure language indexed action prior.
And the results are just undeniable.
Crushing specialist models across the board, like 97.9% on Libero. And astonishingly, it achieves a 26.6% zero-shot success rate on dynamically moving objects in the Domino benchmark.
To truly appreciate the scale of what the Qwen team has engineered here, though, we have to look at why that historical fragmentation exists in the first place.
Right, because everyone just accepts it as normal.
Exactly. If you look at the landscape of robotics right now, the action spaces are deeply siloed. Like, if you are training a manipulation model for a robotic arm, you're probably predicting end effector poses or joint velocities for a highly constrained tabletop environment.
Right.
But if you're training a navigation model, you're looking at waypoints, discrete movement decisions for a mobile base navigating a hallway.
So you have a 7-degree of freedom arm on one side and a 3-degree of freedom mobile base on the other.
Yeah, the prediction horizons differ, the control frequencies differ, the physical constraints differ.
Which means every time you get a new robot, you're basically starting from scratch with a new specialist model. It's a massive bottleneck. It completely prevents embodied AI from scaling up on massive internet data the way, general purpose vision language models have.
But that surface level difference in hardware masks a shared underlying computational structure. Whether an agent is picking up a cup or navigating a room, the fundamental loop is the same.
Observe the world, parse the instruction.
Right. Observe the visual world, parse the language instruction, understand the physical constraints of the current embodiment, and predict a sequence of future continuous actions. The Qwen team realized that if the computational graph is the same, well, the architecture should be unified.
So let's break down how they physically structure that unification, because honestly, framing it as a biological split is the best way to understand the architecture.
The cerebrum and cerebellum analogy.
Exactly. Think of the Qwen 3.54b vision language model as the cerebrum. It handles the high-level cognitive load, looking at a scene, parsing the user's intent to, say, grab the apple, and executing all the spatial reasoning.
But the cerebrum doesn't actually know how to fire the individual muscles to execute the movement.
Right. It passes that high-level intent down to the 1.15 billion parameter single-stream diffusion transformer, the DIT, which acts as the cerebellum. This DIT translates grab the apple into the rapid, high-frequency, fine-grained motor control required across all the different robotic joints.
And the connection between that cerebrum and cerebellum is where the engineering gets very precise. The Qwen 3.5 backbone is natively multimodal, so it's trained with early vision language fusion.
Okay.
To interface with the DIT, the system takes the hidden states directly from the vision language model, concatenates them with a noisy action chunk, and processes them together via joint self-attention.
But the critical piece of this bridge is the use of ADLN, right? Adaptive layer normalization for time-step conditioning.
Yes, that is crucial.
Let's unpack ADLN for the listener, because it's not just a minor detail. If you just inject raw time conditioning into the network, you risk overwriting the semantic features the VLM just passed down.
Yeah, you'd basically destroy the intent.
Right. By using ADLN, the network learns to dynamically scale and shift the activations of the DIT based on the diffusion time step, without permanently altering the raw input features coming from the cerebrum.
It allows the flow matching dynamics to operate cleanly on the action generation side without creating destructive interference with the pre-trained knowledge of the vision language model.
Okay, so having this unified architecture is elegant on a whiteboard, but how does this actually work in a physical tensor?
That's the real question.
I mean, how does one single DIT output actions for a 29 degree of freedom humanoid, a 7 degree of freedom arm, and a 3 degree of freedom mobile base at the exact same time?
They handle this through something called Embodiment-Aware prompt conditioning. It is remarkably simple.
How simple?
The only platform-specific interface in the entire architecture is just a text string. For every training example, they prepend a prompt that explicitly defines the hardware.
Like literally just describing the robot.
Literally, it says the robot is Widow X with single arm, control frequency is 5 Hz, predict the next 16 control actions.
Oh, wow.
The language model processes that string, passes the semantic constraints to the DIT, and the DIT just adjusts its output behavior accordingly.
And for the output tensor itself, they define a fixed prediction horizon and a maximum channel dimension that's large enough for the 29 degree of freedom humanoid.
Right.
Wait, so if they zero pad the extra dimensions for the simpler robots, like filling 26 dimensions with absolute zeros, doesn't that completely wreck the gradients? I mean, the model would waste massive amounts of compute trying to learn how to predict zeros.
That is the obvious risk, and it is why their masking strategy is totally non-negotiable.
Ah, okay.
They implement a per-channel binary mask that sits right in front of the loss function. This mask acts as a physical gate, explicitly telling the loss function which channels actually carry valid control signals for the current robot.
So the padded dimensions are just ignored.
Mathematically excluded from the gradient calculation entirely, yeah. So the model never updates its weights based on those zeros.
That makes perfect sense. The zero padding is just a data container, and the mask is the actual director.
And in their ablations, they tested much heavier projection designs. They tried a multi-MLP approach, where every single robot type got its own private encoder and decoder.
Sounds expensive.
Very. They also tried complex concatenation methods, but zero padding won across the board. It is architecturally the lightest, requiring only a single shared MLP, and it didn't sacrifice a single point of task performance.
Okay, so we have this beautiful unified architecture where the Cerebrum and Cerebellum share a tensor. But putting them together in optimization is basically asking for catastrophic forgetting.
Oh, absolutely.
If you take a highly trained Qwen vision language model and bolt on a randomly initialized DIT, the noisy gradients from the DIT are going to propagate backward and just destroy the VLM's pre-trained weights. How do they isolate these modules to survive training?
They solve this asymmetric optimization problem by framing action learning as decompression.
Decompression, I like that.
Yeah, a short text instruction like pick up the red cup is a highly compressed statement of intent. The model has to decompress that text into thousands of high-dimensional, high-frequency joint position values over time.
Right.
So to manage this without gradient destruction, they developed a 4-stage training recipe, starting with the text action stage, or T2A.
Right, stage 1. They freeze the VLM entirely and only train the DIT. But the most counterintuitive part of this stage is that they train the DIT to predict actions entirely from the text instructions while completely hiding the visual images.
Yep. Blindfolded.
Which is wild. If they were trying to teach the model how to physically pick up a cup, why blindfold it? Wouldn't seeing the spatial relationship between the robot hand and the cup be, the most important part of the learning process?
You're assuming the goal of stage 1 is to solve the immediate physical task.
Well, isn't it?
It isn't. The goal is to build a structured action prior. If you introduce images too early, the model will just take visual shortcuts.
What do you mean by visual shortcuts?
It will look at the pixels, correlate the current frame with the next frame, and completely ignore the deeper relationship between language and kinematics.
Oh, I see.
By hiding the images, they force the DIT to do the grueling work of mapping pure semantic language to raw physical trajectories. It becomes a dedicated language-conditioned action decompressor.
The ablations on this blindfolded training stage are wild to look at, by the way. First, they found that full sequence prediction completely outperforms chunk prediction here because the model has to learn long horizon trajectory coherence without visual landmarks to guide it.
Right.
But the detail that really stands out for anyone implementing flow matching models is the time step distribution swap.
Yes. The shift from the beta distribution to the sigmoid normal distribution.
Let's visualize why this matters for you listening, because it's fascinating. Normally, in image generation, flow matching models use a beta distribution.
Which focuses on the end of the process.
Exactly. The beta distribution concentrates the gradient updates near the clean, almost denoised end of the process. It's like spending all your time polishing the fine textures of a high-resolution image. But in stage 1, there are no visual textures to polish. They are just learning raw kinematic structures.
So they swap to a sigmoid normal distribution, which shifts the learning signal away from the fine details and concentrates it on the messy intermediate noise levels. This is where the broad macroscopic mapping between language and physical movement is actually established.
And it worked so well that performance peaked extremely fast. Like they hit peak performance at just 2,000 training steps.
Which is nothing.
Literally nothing. When they tried to push the training to 40,000 steps, the model actually collapsed and overfitted to the text corpus. So once they lock in that prior at 2,000 steps, they move to stage 2. Continued pre-training.
Right.
This is where they unfreeze the VLM, bring back the beta distribution, and finally turn the cameras on, grounding that language prior in visual observations.
And then stage 3 is supervised fine-tuning, branching into multitask evaluation tracks like Libero and RoboCasa, as well as real-world robot tracks.
Yeah.
But to feed this entire decompressive process, especially the text-to-action prior in stage 1, you need a volume and diversity of data that simply does not exist in standard robotics datasets.
No, the data diet they engineered is a masterclass in heterogeneous mixing. It's 74.2% robot manipulation trajectories, 6% human egocentric video, 7.5% navigation data, 3.7% synthetic VLA data, and 8.5% pure vision language data.
It's a huge mix.
But the inclusion of human egocentric data is brilliant. Wait, human hands have over 20 degrees of freedom. A robot gripper might have 2. How do you mathematically map human dexterity onto a robot claw without confusing the architecture?
They use principal component analysis PCA to extract what they call eigengrasps.
Eigengrasps.
Yeah. By running PCA over massive data sets of human hand axis angle poses, they found they could compress the insane complexity of human dexterity into just the top 10 principal components.
Oh, wow.
These 10 coefficients capture the vast majority of grasping variance. So it translates human video into a unified mathematical space that the model can easily digest right alongside standard robotic joint data.
That is so smart. It effectively lets the model absorb thousands of hours of humans interacting with open-world objects without ever needing a physical robot to collect the data.
Exactly.
They also tackled the labeling problem. If you look at standard dataset captions, they are practically useless for fine-grained control. A caption will just say, "pick up bowl." That tells the model nothing about the trajectory.
To fix this, they built a synthetic pipeline called RoboINF, generating over 8 million synthetic trajectories. But more importantly, they used Qwen 3.6 Plus in a 2-stage pipeline to generate fine-grained embodied action captions.
Right.
Instead of pick-up bold, they generated dense 13-dimensional captions that read like engineering manuals. Things like pick up the ceramic bowl from the right far edge, approach from a 45-degree angle, rotate clockwise for 2 full circles.
Okay.
This dense text is the exact semantic bridge the DIT needs to output precise kinematics.
So supervised fine-tuning, fueled by all this dense captioning and synthetic data, gets us a model that can perfectly mimic a human demonstration. But, as we know, mimicry is brittle.
Very brittle.
SFT optimizes the likelihood of matching a demonstration, but it doesn't optimize for actually recovering if the robot accidentally drops the cup. How do we move from imitation to actual closed-loop success in the environment?
Well, this requires stage 4. Reinforcement learning on flow matching policies. And honestly, this is the hardest optimization challenge in the paper.
Oh, for sure.
They use proximal policy optimization, PPO, with generalized advantage estimation. They attach a lightweight value head directly to the VLM hidden states, applying a strict stop gradient so the value function updates don't propagate back and overwrite the vision language representations.
But wait, how do you apply PPO to a flow matching DIT? PPO fundamentally requires log probabilities. It needs to know the exact probability of an action to compute the importance ratio for policy updates. A standard neural network with a softmax layer gives you those probabilities directly.
Yes, it does.
But a flow-matching DIT is an ordinary differential equation, an ODE. It defines an implicit density through iterative denoising. It traces a single, rigid, deterministic path. You cannot just read the log probs off the output.
Doing so with an ODE would require expensive numerical integration, like Hutchinson's trace estimator, which is, frankly, computationally impossible to run inside an RL loop.
Yeah, way too slow.
So the solution they engineered is a mathematical sleight of hand. They convert the deterministic ODE into a corresponding stochastic differential equation, an SDE.
Let's visualize this SDE conversion because this is my favorite part of this deep dive. Imagine the ODE as a train on a single rigid track. You only see the final destination. You can't easily calculate the probability of the path taken, but by injecting a tiny controlled amount of noise at each Euler denoising step, turning it into an SDE, they basically force the model to leave a trail of breadcrumbs. Each step becomes an explicit Gaussian transition.
And because the transitions are explicit Gaussians, you can compute the log probabilities analytically.
It's so elegant.
During the rollout phase, they store the intermediate denoising states. During the PPO update, they simply reevaluate the velocity field and recompute the Gaussian log probability using standard closed-form math.
Which costs practically nothing.
Almost nothing in extra compute,
Yeah.
But it allows the entire flow matching pipeline to be optimized directly for environment rewards using sparse binary success signals.
Unbelievable. And taking all of this, the unified tensor, the mask zero padding, the blindfolded text-to-action training, the eigengrasps, and this beautiful SDE conversion for RL, what happens when you let this math actually drive a physical robot?
The benchmarks prove that a unified generalist model can thoroughly dominate highly tuned specialists. On the Levero benchmark, Qwen-VLA Instruct achieves a 97.9% success rate.
97.9%.
Wow. On the bimanual RoboTwin benchmark, it hits 86.1% on easy and 87.2% on hard. It outperforms dedicated single embodiment models across the board.
And for those wondering about real-world translation, they deployed it on the Aloha dual arm robot. It hit a 76.9% out-of-distribution success rate.
Yeah, that's impressive.
I mean, it was grasping objects it had never seen during training, like broccoli and toy ducks, all while dealing with entirely unseen backgrounds.
The visual grounding is robust because of the vision language co-training. The model natively understands the semantics of a toy duck, and the massive structural action prior allows it to map that semantic understanding to a novel physical grasping maneuver, completely zero shot.
But for someone who builds robot policies, the result that will truly make you sit up is the domino benchmark.
Oh yeah, the dynamic manipulation.
Domino tests interacting with actively moving objects. Qwen-VLA achieves a 26.6% zero-shot success rate on moving targets. To put that into context, models like PMA and Pi 0.5, which were explicitly fine-tuned on dynamic motion data to solve this exact problem, only scored 17.2% and 7.5%.
It's a huge margin.
Qwen-VLA beat them zero shot. And the kicker, it did this using only current frame observations.
It receives absolutely no temporal motion inputs. It does not track the velocity of the object across previous frames.
Right.
Yet, it intuitively intercepts the target.
How does a robot know where a moving object is going to be if it only sees a single static frame?
It comes entirely down to the incisive nature of the flow matching action chunks. Because the structural prior learned during that blindfolded stage 1 is so deeply rooted in the physical mechanics of the world, the model generates highly coherent trajectory chunks instantly.
Okay, so it doesn't second guess itself.
Exactly. It eliminates the hesitation and compounding errors you see in standard autoregressive policies. The action chunk itself contains the implicit prediction of the object's physics.
So, Qwen-VLA achieved zero-shot interception of dynamically moving targets without any dynamic training data or temporal motion inputs, relying purely on the physics embedded in its text-conditioned action prior.
Yeah.
If a model can predict precise physical interceptions using only static frame observations and a strong structural prior, what does this actually imply for the future of world modeling? Do we really need to build computationally massive video predictive world models for embodied agents? Or is learning a highly structured language indexed action prior sufficient to unlock intuitive physics in real time?